Hello, everybody. Welcome to today's Courant seminar. Today we have two speakers, two talks. Our first speaker is Dr. Yiping Lu. He will be giving a talk on simulation-calibrated scientific machine learning. Yiping Lu is a Courant instructor at Courant Institute of Mathematics Sciences, New York University, and an incoming tenure-track assistant professor at Industrial Engineering and Management Science, Northwestern University. He received his PhD degree in applied math from Stanford University in 2023 and his bachelor's degree in applied math from Peking University in 2019. Yiping was a recipient of the Conference on Parsimony and Learning Rising Star Award in 2024, the Rising Star in Data Science from the University of Chicago in 2022. He also serves as an area chair for flagship machine learning conference, such as AI stats. With that short introduction, the floor is yours and you can start your presentation.
Thanks for the invitation and for the talk. So today I will share like some ongoing work of my recent research. So I think I don't need to spend time to talk about like the background. So we want to combine like the physics we have written down by the mathematician and the data collected from the experiments to have like a machine learning, physics informed machine learning program. So the thing I'm truly working on is I want to understand like this program like theoretically. So how can we combine these two disciplines to have some benefit like provably? So this is the thing I'm always trying to work on. And today I would like to show you like some new result. So the thing I'm actually worked on is wants to characterize some like the optimal physics informed machine learning. So we want to know like under our physics model, for example, we have like a equation like AU equals to F. A can be the differential equation, and the U is like the solution of the differential equation, and F is the right-hand side. So how we can do like optimal information how we can do optimal information collection and design an optimal algorithm to recover all the information from this equation. So the task we are working on here, so yes, you all very familiar with. The first one is physics-informed machine learning. So in this framework, the physics-informed machine learning can be written down as we collect like the data of the right-hand side, and we want to reconstruct the PDE solution U. So this is you can consider this as an inverse problem or just solving on PDE, and inspired a lot of research, not just physics, also beyond physics, like mean field game, auction design. So they are all like physics-informed machine learning approach to reconstruct information from a physics equation. And the second one is the operator learning. So we want to learn the operator directly maps from the right-hand side to the left-hand side. And the third task, I want to know what is the optimal thing, what is the optimal information theoretical limit is the inverse problem. Maybe in the PDE operators, we have some parameter theta, and I want to infer the theta using the observations. So during all my PhD, what I'm working on is I want to write down what is the lower bound of these three tasks using some information theoretical techniques, and also wants to show that nowadays the already developed physics-informed learning, whether the algorithms are optimal or not. So during this line of research, the thing we want to do is to bring something from information theory. We want to know what is the optimal physics-informed learning algorithm in the min-max sense. What is the min-max sense here means we want to know, like we want the physics-informed machine learning to work for a class of problems. And for this class of problems, we want our algorithms works for the worst case, that is that our algorithm can perform uniformly good over a group of functions, and I want to know what is the best estimators. So this is just a broad from the information theory. But for the information theory, most of the people are working on just fitting a function. But for now, we want to plug in our three tasks like physics-informed machine learning, operator learning, inverse problem into this framework to see how we can do optimal computation for the scientific machine learning. So in the previous few years, we have several progress on these directions. So we find out that the physics-informed neural network is somehow optimal estimator for solving a PDE, but some machine learning algorithms such as deep reason method is not. And also we extend our result to non-IID data. And also recently we show that physics-informed machine learning is a more interesting thing. Is we know if we have like a very large over-parameterized machine learner, if we want to interpolate all the data, everything will do an overfitting. Recent research shows that if you are in high dimension, then you can do something called benign overfitting. Just that although we interpret all the data, we still can give the right solution. But we show that with physics-informed machine learning, we can actually remove out the high-dimensional assumptions. We show that if you do a physics-informed learning, you can still have benign overfitting even in a fixed dimension without the high-dimensional assumptions. So this is our recent work. So we already get a lot of things from these directions, but I ask myself that question. So I have proved a lot of theorems that, okay, many of the machine learning algorithms can optimally solve a PDE, but do I really trust my theoretical guarantee? So the answer is not. It is obvious that we make so many assumptions. For example, in one of the paper I proved physics-informed neural network is optimal. I assume that we can do global optimization of the complicated landscape, which is a very hard task in practice, but which is also NP hard in theory. And maybe we also assume that the function have some very strange structures. So beyond the smoothness, so if you want your neural network to globally converge, you will always assume that the f have some very strange structures that in the realistic, it doesn't satisfy. And also we also made assumptions, for example, the neural network is wide enough, so which is not always the case, the wide enough, which is not achievable in practical sense. And even all these assumptions satisfied, the theorem we write down is just a big O. Maybe the big O is a big constant here, so we can't actually trust the guarantees that we have provided for the optimal machine learning algorithms. But for today, I want to show you that there is actually exists a subclass of scientific computing problems where we can show that even with biased machine learning predictor, we can do unbiased and trustworthy prediction. And we can also show it is optimal. So for today, I will introduce you a new framework that we feel very, very excited about, which include many, many examples we have shown. We call it simulation-calibrated scientific machine learning. So the idea is we have a scientific machine learning algorithm. Maybe it is biased. Maybe we don't have any guarantee on yet. We just run a trustful algorithms that to calibrate the wrong solution or biased solution provided by the machine learning algorithm. After the calibration, then the solution will become unbiased and better. And we further prove that if your scientific machine learning algorithm in some sense is good, then the algorithm we provided here is also optimal. So this is today's talk's aim. So we want to show you there is actually a possibility to do unbiased prediction with a biased machine learning predictor. So how can we do this? So the subclass of the problem we are considering is not like a scientific machine learning. So for machine learning or scientific machine learning, we can write down it as the framework like this. We first collected some data, x1 to xn, which is sampled from a distribution that is parameterized by a parameter theta. And we use a machine learning algorithm to recover what is the theta hat. So this is the machine learning. For example, we can do function fitting in this framework. We can do PDE solving in this framework. But for today, we consider one step further. After we solve the PDE, it is not our application. In the application, we will always consider that we will use the solution we solved from the PDE to do another downstream application. So for now, we are not aiming to solving the theta hat, but for now, we want to solve some downstream application like phi theta hat. So this gives us some possibility to have some better algorithm. The reason is the theta hat in the PDE task, the theta hat is a function. So it is high dimensional thing, right? Infinite dimensional thing. But if your downstream application, for example, it is some successful rate, or it is some momentum like the temperature, like the speed, then it is just a real number. So predicting a real number is much easier than predicting an infinite dimensional thing. So this gives us some possibility to do the unbiased prediction here. So maybe our first step prediction is biased. But while we do the downstream application, we can utilize the physical structure in the downstream application to calibrate the bias in the first step. So let me show you how we can do this. So to do unbiased prediction, the only thing you need to do is to calculate what is the bias, right? So if we can have an unbiased estimation of the bias, then we can provide an unbiased prediction. So our aim here is to debias the solution of your naive downstream application. So we first do a naive downstream application estimation, but we still also want to give an unbiased estimation of the bias provided in the first step. So we only need to give an estimation of the bias here. So our idea is to use.
Yiping, can I ask a question?
Yes.
Okay, so how is this different from saying that you are going to estimate the uncertainty associated with the epistemic uncertainty associated with a neural network?
Okay, that's a very good question.
Is it exactly the same problem or not?
I think it's not the same problem. So if you want to estimate the uncertainty, you are still like working on the theta hat. But now if you at the later of the talk, you can see in my framework, if you can work, you can go through, then the only thing you can go through is you have this phi. So I think in the later you will see they have difference. They have the difference. Yeah.
But what you're talking about biasing?
Yes.
What caused the bias?
That's a good question. So for example, if I train a neural network, I don't train it to I do an early stop, then I have a bias, right?
Right,
So
but
like,
that's exactly what I said. The uncertainty,
yes,
the epistemic uncertainty associated with a neural network is exactly the same problem. You're trying to capture it. Never mind if you cannot actually do it, but in terms of a target, I think you have the same target.
Yes. So
it's the epistemic uncertainty associated with all the hyperparameters for that neural network, and the selection of that.
Yeah. Let me try to answer a question like this. So like if you want to estimate the uncertainty, the thing you want to estimate is still like working on the theta hat. So you still want like to do this hard question. So for here, I actually do a little bit cheating. I just work on this easier question. So in the later of the talk, I will show you when you do the easier question here, I can provide a much stronger guarantee than what you do just on the theta hat.
Okay, but conceptually, you're after the same problem. Never mind how you do it. The target is the same.
Yeah. Yes. You can consider like this. Yeah.
Okay. Thank you.
Yeah, that's a quite good question. So in the later of the talk, I think I hope everyone can see that the phi here is a very important structure that we can do everything here. Yeah. So now the question is how we can compute this bias and why it is easier so another question, the first question is how we can compute this. It's like how we can do the debiasing. And the second question is, if you can compute this, I can also don't do any estimation in the first step, right? I cannot compute the theta hat. I just naively gives you a random guess of my theta hat, and I can directly estimate my phi theta hat. So why the theta hat here will help you to do the prediction? So here is the answer. The first thing is why I can do like this very good estimation of the bias. It is because I will utilize the physical structure of the phi. Like the phi is a very special kind of PDE, or phi have very special kind of functional. And the second thing is because we use a stochastic simulation algorithm to do the estimation, then if you do a good estimation of the theta hat, then the theta hat will provide a good variance reduction. So I will show you these two things in the following very easy example. That still doesn't consider like complicated PDE case. We just consider the function estimation case. So in the first step, I want to estimate the functions. But finally, I just need to know what is the temperature, what is overall velocity, which is just the higher order moments of the function. So how can we do this? So let's say what if we first use a neural network or any estimator you can have to estimate x hat to estimate my function f and then compute phi. What does this mean? So this means that if I want to estimate a function's mean, I first estimate my function and then I compute the exact mean. So this is nothing new. This is just like if you use the f hat using a piecewise polynomial, then this is just the Simpson's rule. Then let's show you what's the thing I will do beyond the Simpson's rule. The things I will do is I will estimate what is the bias of the Simpson's rule. So I use another half of my data set. So I have another half of my data set. So on my another half of the data set, the thing I know is I know the function value because this is from my data set. And the second thing we know is we also know the function value of the f hat. So we can compute the difference between f and f hat. So we know what is the error of my f between f and f hat here. I know what is the error between f and f hat here, and what is error between f and f hat here, and also here. And then I do an average. Then we can know what is the actual, what is the error of the first step estimation. So this is like a very easy change to the Simpson's rule that can give you actually a much faster convergence rate. I will show you later. So here, so I just tells you an example. So if your functional phi here is a linear functional, then we can use the Monte Carlo method to do the debiasing. So why this method is much better? So let's consider if you just do Monte Carlo method. Let's say we don't do the Simpson's rule, we don't do this function approximation or machine learning algorithm. We just directly do the Monte Carlo estimation. You can also compute out my phi, right? But in this case, the variance of the algorithm is actually the variance of my f. So this, in the worst case, it must be an O1 thing. But in the previous case, we already have like a function f. We already used the machine learning algorithm to predict the most thing, like the most rough thing of my f. Then the variance here is just the variance of these very small residues. The variance of this part is much smaller than the variance of this part. So I show you that if I do a better machine learning estimation, then I can do a much easier Monte Carlo estimation in the second stage. So in mathematically, we can formulate this problem like this. So what I'm doing here is actually I want to combine two types of algorithms. So in the first type of algorithm, I want to estimate my expectation like of a distribution P of f. So I can write down the integral of this. So the first thing is, the first algorithm is the Simpson's rule. The Simpson's rule says that, okay, let's use a machine learning algorithm or function fitting algorithm. First, approximate my function f using an f hat. And then we do the exact integral. So this is what the Simpson's rule doing. But what is the Monte Carlo algorithm doing? So the Monte Carlo algorithm doing is, okay, let's just sample some p. We just replace my p with a p hat, but we do the exact thing of f. So this is just like we want to do an estimation like x times y. The first thing is, okay, let's do an estimation over y to have a y hat. Then we compute x, y hat. The second algorithm said, okay, I want to compute x times y, and then I just do estimation on the x, so this is x hat times y. So this is two types of algorithms. So I think in the literature, there is a long debating saying that, okay, the Simpson's rule is good for low dimension, Monte Carlo algorithm is good for high dimension. But this simple thing tells us that these both claims here are wrong. So you can actually combine the Monte Carlo algorithms with the Simpson's rule to get algorithms that are better than both. So let me show you what's the thing I'm doing here. So I construct a debiasing term like this. Then if you do an estimation on the y, then the error here is y minus y hat. If you do an estimation on x, the estimation error is x minus x hat. But after you do a debiasing, then the error here will become y minus y hat times x hat. So if you have a convergence rate for the first algorithm is to the alpha's power, you have a convergence rate to the second algorithm is to the beta's power, then my algorithm here will provide convergence rate is alpha plus beta, which is an algorithm probably faster than both. So this tells you that the Monte Carlo algorithm and the Simpson's rule or function fitting is not like we should compare them or we should say which algorithm is better in which regime. So it is the simple answer is we can achieve an algorithm that is both better. We can combine them to get an algorithm that is better than both. So here is a question. So is there anything particular to machine learning for this? So no. So you can do any data-driven model. So or even not data-driven model, you can just do spline fitting, any function approximation algorithm. So there is nothing special to the machine learning here. Yes. So then I can show you also a second example. It is not like machine learning even. So the example is to do randomized function to do randomized numerical linear algebra. So the randomized numerical linear algebra, I can also written down this in my framework. So the randomized linear algebra, the problem is I have a matrix A, but I don't know what is my matrix A. What I can do is I can have some random or design xi, and the thing I can know is what is my matrix times my xi, because the matrix times a vector is fast. This is the only thing we can do to deal with the matrix. All the other operations to the matrix is slow. And then we want to know what is for example, what is the trace of the A. So the previous algorithm said, okay, if you want to estimate my A, you can use algorithms like randomized SVD. Then you can provide a good estimation of the A hat. But the best algorithm to compute the trace of the A is not to directly compute the trace of A hat. So there is a work by Lin Lin in 2017, and the following work from David Woodruff's group 2020 shows that the optimal algorithm to solve this problem is we first compute the trace of A hat, and then we use a Hutchinson's estimator to estimate the error of trace of A minus A hat. So this algorithm is called Hutchinson++, which is proved to be the optimal algorithm to compute the trace of A. So you can see the idea here is not just to do function fitting. You can use this idea to do many of the tasks, and I will show you the idea later. So the examples will include high-dimensional PDE solving, large-scale linear equation solving, and uncertainty quantification. So the first example I will show you is uncertainty quantification using bootstrap algorithm. So in this example, the uncertainty quantification and the bootstrap is not like very important algorithm we are using. This is just like an example of another big idea is I have a cheap algorithm and I have a expensive algorithm. The cheap algorithm is bad, but the expensive algorithm can do better job. The idea here is we can actually combine the cheap algorithm with the expensive algorithm. And then we can use almost the same cost as the cheap algorithm, but achieve almost the same accuracy as the expensive algorithm. How can I do this? So here is the example of the bootstrapping. So let me first give a very quick introduction of what is bootstrapping doing. So the bootstrapping thing is considering I have a true data distribution, P, and I want to estimate some F of the distribution P. But in the real application, what I can get is just some empirical data distribution P hat. So the estimation you get is F P hat. As we said, the P hat and the P is not the same. So I want to say my FP should lie in an integral that between FP hat and minus delta and FP hat plus delta. And I want to know what is my delta, which is the variance of the algorithm. But the variance of the algorithm, we can never estimated it. The reason is I can just have one empirical data set. I can't have several empirical data sets. Then the beauty of the idea of the bootstrapping is that the true data distribution and the empirical data distribution should be very similar. So if you want to sample the empirical data distribution multiple times, it will very, very similar to you just resample the data from your empirical data set, because the empirical data distribution is very near to the true data distribution. So to estimate the variance, the thing bootstrap algorithm do is, okay, we resample another data set from my empirical data set, and then resample this for many times. And we calculated the variance of the resampling procedure. And this variance should be very, very similar to the variance here. So the theoreticians have proved the good thing for the bootstrap is it is a very high order approximation to the variance. So it can provide high order coverage of the confidence interval construction. And the bad thing for it is the number of bootstrap resampling should proportion to the number of data. So let's consider we just do a very small scale machine learning where we just have 1,000 data, okay? So we train a neural network over the 1,000 data. But this theorem says that if you want to get a bootstrap result, you should resample the data set for 1,000 times, and we should retrain 1,000 neural network to proceed the variance of your algorithm. So this is not acceptable even with 1,000 data, because you need to redo your machine learning training for 1,000 times. So our answer is, can we do like 01 times of resampling to get the same result as the bootstrapping? So this is how we formulate this problem in our framework. So let's consider the first step is a very crazy fitting. The crazy task is we want to map the data distribution to the output. So it is like we want to map a data distribution to the neural network we have trained. So this is a very, very crazy work. But this stage is almost very hard to achieve. But the second stage is we just need to know what is the variance of it. So the first stage is a mapping which maps from a distribution to a neural network. So it is a very complicated mapping. But the only thing we need to estimate is actually a real number, which is just a variance. So this makes this task possible. So let me show you how we can combine a cheap algorithm with a hard algorithm. So the thing we are doing is in the first stage, which maps from the data distribution to the neural network, we just use a linear approximation. So this linear approximation is nothing new, which is known as infinitesimal jackknife in the literature. So you can consider here the infinitesimal jackknife is a biased algorithm, but it is a very cheap algorithm because it is just some linear computation. We just need to compute some matrix computation here. Then we can know what is a biased approximation to the variance. But then we know that for every approximation here, we have a phi hat, which is a linear approximation over like the mapping from the distribution to the neural network. But then we still retrain several neural networks. So we can retrain several neural networks which approximate the phi with phi hat. And then we know what is the bias caused by the cheap algorithm. So here is our recipe. We run several cheap algorithms. We run a lot of cheap algorithms to get the expectation of the cheap, the mean of the cheap algorithm. And then we just run several hard, expensive algorithms, and we approximate the difference between the cheap algorithm and the expensive algorithm. And we collect all these things out, and we debias the cheap algorithm. So this looks like a very, very naive idea. But in our paper, we proved something very interesting. So we proved that if you do this, you can do high order coverage as the previous thing. So you can have the same theoretical guarantee as your bootstrap algorithm. But the good thing is now the resamples, like the bootstrap resamples, you just need to do 01 times. We can prove this. So this is like we run a cheap algorithm, which is called infinitesimal jackknife, and then we just need to do O1 times of the expensive algorithm, which is the orthogonal bootstrapping. Then we can do the same guarantee as the bootstrap. So let me show you the simulation here. So this is like a very easy simulation because we have closed form solutions. So for these examples, you can see if you just do like 2 times of bootstrap or 5 times of bootstrap, the bootstrapping can provide you very bad coverage. So you can see the coverage here is just 50%. And if you do 5 times of bootstrap, you can just guarantee 80%. But if you do our algorithm, so our algorithm can provide you almost 95% for most of the examples, even with just the 2 times of the bootstrap. And there is also another recent work 1 year ago called cheap bootstrap, also want to do the same thing. But their idea is because our bootstrap have another variance. So they add the bootstrap variance to the confidence interval. So they will provide a much longer confidence interval. So you can see the cheap bootstrap will provide longer confidence interval to guarantee 95% coverage. But our orthogonal bootstrap still gives the same length as the bootstrap. So you can see if I do like many times of bootstrap, the confidence interval length here is 0.07. So even with 2 times of bootstrap, we can still give the same length here. So they are the same length. But we can still provide you the 95% coverage. While the cheap bootstraps, they provide the 95% coverage, but they will enlarge the confidence interval. So we provide the smallest width of confidence interval, but still with 95%. It is because we are approximating like what is the true bootstrap algorithm working. So this is a neural network example. So for the neural network example, you just need to retrain your neural network for twice, and then you can get almost like 95% coverage. So this is a very amazing result, shows you that if you have a cheap algorithm, you just work out everything of the cheap algorithm. Then the expensive algorithm just used to correct the cheap algorithm. You can get the same guarantee as the expensive algorithm, but computational cost at the cheap algorithm. So this is the example I want to show you, like how like this or the SCASMO idea can be used for even like very different applications. So all the previous example I have showed you before, the phi is somehow linear. We can use Monte Carlo algorithm to simulate it. In the first example, it is an expectation, and in the second example, it is a variance. And then in the next 2 examples, I will show you some examples of nonlinear phis. So for the nonlinear phis, I will show you 2 examples. The first example is we use an iterative algorithm to approximate phi, which we use it to solve high-dimensional PDEs. And the second is we use a Taylor expansion to approximate phi. We use this to design some randomized linear solvers. So let me show you the first example is a high-dimensional PDE. So for solving PDE, we can also write down this in our framework. So in our framework, we write down this as like, okay, we want to solve equation Laplace equals to f. Then the data we collect is just xi and the value of Laplace u xi. The parameter we want to recover theta here is the u. And you can use like physics-informed neural network, deep Risk method, neural Galerkin, Gaussian process, or even just a sparse grid or anything you want. A finite element is also fine here. So you first do a function approximation in the first stage, and then let's ask a question. What if I just want to know like the mean of the PDE solution, the variance of the PDE solution, or I just want to use the PDE solution at a single space-time point? Okay, so for this case, this is just a real number. But for the previous task, it's much harder. The previous task is I want to approximate the whole PDE solution, which is an infinite dimensional thing. But now I just need to know the mean, the variance, and like the solution at a single space-time, which is just a real number. So let me show you how we do this. So we first use like physics-informed learning to learn the approximate solution. And then we do a scarce-mode debiasing. The way we do this is to write down another equation that the residue satisfy, and we use a simulation algorithm to solve that. So the warm-up example is quite easy. Let's just consider the Laplace U equals to F. So if we consider the Laplace U equals to F, so we have the Laplace U hat equals to F hat. If we minus these two equations, we have the Laplace U minus U hat equals to F minus F hat. So if I want to solve this equation, it is easy. I just need to do a Brownian motion. So we do a Brownian motion simulation here. We just need to collect all of the F minus F hat here. But if we don't have this F hat, the thing we need to collect is F here. But once we have like physics-informed neural network prediction F hat here, the thing we need to collect is just to collect the error of your pin. So the algorithm is here. So we first train a pin, and then we collect the error of the pin through a Brownian motion, and use this to correct the error of the pin. So you can also do this for the mean or variance, but this is not the hard part. The hard part is how we can deal with the nonlinear equation, right? So the thing I'm dealing with here is a linear equation. So we can have this very good structure. So the answer is we can't do every nonlinear equation with this procedure, but we can do the semi-linear equations. So if we do a semi-linear equations, we just need to use the linear thing of the Laplace. So we can just write down all the nonlinear thing here as a black box, and we can still do this minus here, because the Laplace is linear operator. So if you minus two semi-linear equations, you can get another semi-linear equation, but we put all the nonlinear things just as a black box. So the only thing change is that the nonlinear terms will change, but it is still a semi-linear equation. So you can use this structure you can see the semi-linear thing can be preserved. And then we use something called multi-level Picard iteration, which is a simulation algorithm to solve high-dimensional semi-linear heat equation. So we use this like Monte Carlo algorithms called MLP to correct the pin for the semi-linear heat equation. So let me show you some numerical results here. So we solve a 100-dimensional PDE here. Sorry, I forgot a bracket here. So this equation have a closed form solution so that I can test it. So this is the error of the pin. This is the error of a multi-level Picard iteration. And if I do a scarce-mode algorithm, it is an algorithm that can provide better algorithms than both pin and multi-layer Picard iteration. So another thing I want to point out is the comparison between MLP and PIN is not a fair comparison. The reason is PIN can provide prediction for every place, but MLP can just provide the prediction at a single space-time point. So this is not a fair comparison to compare the PIN and MLP, because MLP and the scarce mode are just provides you are just doing a simple task, but there are exactly some tasks in financial engineering and control just needs the solution at a single space-time point. Because if I want to control something, I just need to know the PDE solution at the points that we achieved. We don't need to know the PDE point at every place. So this is the application we are considering about. So you can see if we just consider this case, the PIN can help to reduce the variance of an MLP. So this is for so this is 100 dimension, and this is 250 dimension. So you can see while we scale up the dimension, the MLP will become less and less robust. But the PIN still remains the same level. So we use the PIN can use as an approximation to debias the MLP and get better estimation. So you can see the scarce mode algorithm here is an algorithm can provide both more accurate estimations than both algorithms, as we discussed in the previous expectation estimation thing. So for the theory of this one, I will just put it at the end of the talk. So this is how we do this. So we first solve a PDE, and then we use from emotion simulator to crack it. So I will use another 5 minutes to tell you another. So there are also a lot of related work that combines the PD solver with neural network. So I want to discuss that like the related works, but actually myself personally still doesn't have a very clear information about that. The only thing I know is I tried to prove the combined estimator is better than both of the estimator. Or my framework here is the only thing I can prove to get a better rate. But for all the others, I tried, but I don't success. Maybe I'm wrong, or maybe there are other reasons. So I will discuss this later. Yeah. So I will use another 5 minutes to show you I can also use this to design a randomized linear solver. So for the linear solver, I have said that the randomized linear solver sketching algorithms, I can write it down, also use our framework. But now the 5 here is like the trace, the eigenvalue, or maybe some A inverse X. So, but let's consider the eigenvalue and A inverse X because they are nonlinear functionals. So they are nonlinear functionals, so they are harder than the linear functionals. So our answer is here. Although it is a nonlinear functional, we can do a Taylor expansion. So we can write down the difference between the sketched solution and the original solution. And you can see, you can write down the Taylor expansion and you can truncate it to do the debiasing, and you can always prove it can give you a faster convergence rate. But this is not a new algorithm for the inverse. For the eigenvalue estimation, it is a new algorithm, and we are writing down the paper. But for the sketching to solve like A inverse, it's not a new algorithm. So one of my clever students find out that I previously think this is a new algorithm, but my student told me, okay, if you do a clever, if you do a more detailed computation of this, you will find out that it is actually the same as iterative sketching. You can consider this algorithm is I want to solve A inverse X, then I try to do a Newton method. But for every step, I can't solve the true Haitian, so we just sketch the Haitian. So it is called iterative Haitian sketching, so it is just a sketched version of Newton iteration. So mathematically, these two algorithms look very, very different. But if you do a careful calculation, you will find out that these two algorithms are the same. So these are very, very interesting result. And the reason is if you do a Taylor expansion to the inverse here, it means you are using this numeric series to do the approximation. Then you will find out that these two things are the same. And the second thing is this is also not a new algorithm in another sense. So it is because it is a Jacobi iteration here, right? So if I want to use a Jacobi iteration to solve this, this is the Jacobi iteration. So you will find out that this is also equivalent to you use your sketched version as a preconditioning to the Jacobi iteration. So it is that our algorithm is the same as iterative Haitian sketching and the sketch and the precondition. Okay, so it is not a good algorithm. So sorry, it is not a new algorithm, but we can still tell you some insight of some numerical linear algebra. So in numerical linear algebra, it is known that the sketch and precondition algorithm is not stable. The reason is, the fact is, if you add some noise to your B, it is that, okay, my AX is not equal to B. The least square solution is not like equal to 0. You just add a very, very small perturbation here. Then the sketch and the precondition algorithm can give you the best estimation. So this is found by a recent work, and they do extensive numerical results, shows that if your A have like a very large condition number and your AX is not exactly equal to B, then the sketch and precondition will always not find the best answer. So we have another view of this. So for the iterative Haitian sketching I have introduced before, the idea of that algorithm is, okay, let's run a Newton's method. And so it is an iterative algorithm like this. But I have shown that the thing we are working on is actually we are doing a debiasing stage one by one. So this is not the efficient way to do the debiasing. The most efficient way to do the debiasing should look like this. So if we do a first time iteration of the algorithm, and then we do the debiasing to my algorithm and get my second step, right? And then we can directly do the debiasing over my second step. So we directly debias over this guy using the same algorithm here. So it looks like the previous one is a sequential algorithm, but for here it is a recursive algorithm. So if I write down the mathematical thing to show this like very easily, you can see the equation here. So the previous algorithm is calculating I plus a squared plus a to the third power. The thing we are computing here is I plus a squared, and I plus a to the fourth power. Because now this is the first algorithm, and then we debias it using this algorithm. And then now we already have this algorithm. We can use this algorithm to do the debiasing, and then we can directly go to this step. So these two algorithms have the same computational cost, but the interesting thing is the previous algorithm is not this algorithm. IHS is not is not stable, but if you do iterative debiasing, you can prove it is stable. So here is the thing we can show. So although they will gives you the same iteration here. So you can see this is the forward arrow, this is the residual arrow. But for the stability, if you compute out the backward stability of these two estimators, the iterative debiasing is much better than iterative Hessian. So you can also you can also examine it to check the KKT condition. So the KKT condition of the least square is this guy should equal to 0. But if you run an iterative Hessian sketch, so for large condition number, you can see this thing can't convert to the machine precision. But if you do iterative debiasing, although they compute out the same iterations, but the iterative debiasing will provide you a much stable sequence. So this thing will converge to the machine precision no matter how large is the condition number. And we compare this to the MATLAB function. Our algorithm is even better than the MATLAB, like the /b. Our algorithm is actually better than that. So we also compared our algorithm with a much computational harder algorithm. We achieve almost the same level of backward stability. So I don't have time to go into the details of that. I just show you that our idea can be used for the randomized linear solver. So for the last 5 minutes, I will quickly go through our theory. So I will also show you that if you have like a optimal machine learning algorithm in hand, the procedure of the SCASMO is also an optimal algorithm. So the setting we considered here is we consider to estimate the moments here. So let's consider we have a f is a smooth function. Let's say f is a Sobolev function. And we want to show that the estimation algorithm we provided in the previous sections, they are all optimal. So let me directly tell you what is our answer. So we consider the case. So sorry, I will directly go to the answer here. So we consider the case that the Sobolev space have the potential is out of L infinity. It is that my function is not embedded in L infinity. So we use the Sobolev embedding to show you there are two regimes of our algorithm. So if our algorithm is smooth enough, then using the Sobolev embedding theorem, you will show that our function will be embedded in an L infinity space. It is that our function will not have a spike. So if your function is not smooth enough, then our function can't be embedded into an L infinity space. It is that, okay, our function have a possibility to have a spike. So there are two regimes. One regime is it have a spike, and another regime is it doesn't have a spike. And our result shows a phase transition of whether you should use a Scasmal algorithm. So if you want to use a Scasmal algorithm, the regime should be the spike of your function have a finite variance. So you can see the phase transition point happens at the convergence rate of half. So if your algorithm, if your spike like have a finite variance, then you should use a machine learning algorithms to reduce the variance of the simulation algorithm. Otherwise, it is you should do a variance reduction using a machine learning estimator. But if your spike have infinite variance, then you should do a truncated Monte Carlo, because the spike itself have an infinite variance and your machine learning algorithm can't approximate this spike. So you should truncate your spike to let it to have a finite variance, and then you should do a bias and a variance trade-off of like, if you do a truncation, then you will have a bias, but then your variance will become bounded. So you should do this kind of bias and variance trade-off proof to show that the truncated Monte Carlo is already optimal. So here is like the phase transition of whether your spike have finite and infinite variance, and what is the meaning of this spike. So your function have a spike in the real world, it means that your event have a real event or not. So the spike is like a rare but very extreme event. So our take-home message is here. So the take-home message is when you should use, so we have a very beautiful proof here, but we don't have time to go through. So I will just tell you like the take-home message. So the take-home message here is, so if you have a rare and extreme event, okay, so if you have a real and extreme event, your real event have infinite variance. Then the hardness of the problem is dominated by whether you should truncate your real event. But if you don't have a infinite variance real and extreme event, your function looks like the left-hand side, then the Scasmal is the optimal algorithm that you should go with. So this is like take-home message. And let's just summarize what I have talked about today. So for today, I consider an easier question. So I don't consider I recover phi hat. I consider another downstream application like the moments, like a PD solution at a single space-time, like A inverse X, like eigenvalue. We consider phi theta here is just a real number. So it is a much easier task than you recover a high-dimensional theta hat. Then you can use the idea of the biasing to compute out the bias, and using a Monte Carlo algorithm to compute this out to do the debiasing. The example I showed you includes the quadrature rule construction, trace estimation, high-dimensional PDE solving, large-scale linear equation solving, and uncertainty quantification. And I want to work on more applications. So if you have your application is in your hand, you think might have the possibility to write down in this framework, we can try to work together to show whether we can write down the biasing algorithms. And also theoretically, I also want to know whether this procedure, we can have a meta theorem to show that this procedure can be worked out for many of the examples, not like I will analysis one by one to show the optimality. So I think this is all for today. And if you have, we can have the last 5 minutes to do the Q&A. Yeah, thank you all.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Hi, Yiping. I have a question on the, so you, in all the applications you have as a downstream application, a function, because you want to limit the cost, I suppose. Okay, but in my application, I have to reconstruct a flow field from some sparse measurement. So I need to, so I do a pin, and I need to do that everywhere, not in just a small 1 point or a few points. I need to do, so in that case, it's very expensive, right? Because you have to do that point by point. Yeah. That's why I said earlier, then other methods like an uncertainty quantification, lots of them, Bayesian and ensemble methods, can actually give you an indication of what that is. Now, if you can use it as a boosting method to improve the accuracy and so on, you can, because if you estimate a error, you can put it back on the right-hand side and do the booster method. But anyway, I'm just trying to I guess you that's why you sort of targeted a downstream application where there's one. Yeah. Okay. So because of the cost,
Yeah. So I have another like explanation to this. So if you just consider like predict everywhere, because I have already proved the PIN is the optimal algorithm. So even you do a boosting, you can just have constant time improvement. You can't have rate improvement.
Right.
So
right.
to avoid this, that's why I introduced a downstream application. So to introduce the downstream application is the only possibility to improve the rate. Yeah, so I think that's my different focus. Yeah.
Okay, thank you.
Yeah.
I see Costas from all the way from Italy has a question.
Thank you, George. Yeah, this is Costas from University of Naples. Thank you for your presentation. Actually, I would like to ask about your approach. It's relevant to George's question. You saw things where phi is kind of nice and smooth. And you saw at the end some rare event. I mean, some very simple regression problems with phi. For example, take the logarithm of 1 minus x1 minus x2, right? So at the beginning for x1, x2 close to 0, you have a nice 2D manifold where this transforms to 1D manifold near singularity. There, I mean, your bootstrap kind of all this framework, you will not have all this nice data X to do this. I mean, can you comment on this?
Yeah.
I mean, this is also nice problems of interest, because when things are smooth, I mean,
Yeah, so that's a very good question, because when I'm dealing with my phi, nonlinear phi, I always assume some like regularity. For the Picard iteration, you should have like contraction, right? So if you do Taylor expansion, it should be smooth. So this is a very good question.
Yeah, exactly. Yeah, because you do Taylor expansion where near, not so near to the singular points. I mean, if you take this example that we have published, this J-confis, I mean, not so near to the singularity. I mean, you will have hard time to do this.
Yeah, so these are very good questions. So what will happen if we have like some non-smooth phi? So first of all, we can imagine we can't do like any non-smoothness. We can just do some of the non-smoothness. This non-smoothness still have some structures. So this should relate to some variational analysis. You will assume like phi is some kind of smoothing after a proximal. So this is most of the case your singularity will satisfy. For example, constraint method, you have a manifold, then you can try to do a proximal method, then it will become smooth. So then the answer maybe you should define the Taylor series in the proximal sense. I think there is a long line of research on this in like non-smooth analysis or variational analysis. It works on that. So you should try to do a proximal on phi. I think there are recent works. I have read that. So there are recent work try to combine the proximal method with the bootstrap to gain some guarantees for the non-smooth part. Yeah.
All right, great. Maybe I will send you the work. This is also with Yannis Kevrekidis, so you can take a look. It's in different context, of course, but you can see the difficulty of this. Okay, thanks.
Sure.
Thank you so much. Do we have any other questions? I can see one microphone on. Liu, do you have any question? I think there is no more questions, so it's time to move on to our second session. Thank you for your great talk, and thank you for accepting our invitation. Dr. Abbaszadeh, can you hear me?
Yes. Do you have my voice?
Yes. Can you share your screen to see if there is any problem with the presentation?
Yes, my student will present Rauf. Do you?
Rauf, are you here?
Please. Rauf, please give access.
He has the permission to share the screen. Ralph, can you hear us?
Hi, everyone. Can you hear me?
Yes, sure. Can you share your screen
Yeah,
for the
of course.
presentation?
Just let me a second. You have my screen?
Yes, can you put it on presentation mode, please?
I'm sorry. Can you repeat again? I could not hear your voice, and I think
Can
there's
you?
problem with my connection.
Yeah, I know. Can you put it on presentation mode?
Yeah, of course. Just
Thank
let me
you so
to,
much.
it's kind of new for me because I'm not familiar with Zoom, but
I see.
just with me. And is this in the presentation mode
Yes.
now?
And
All right.
do you have any video to play or
No.
something
No,
like
there's
that?
no video.
Okay, thank you so much. But here I have the biography of Dr. Abbaszadeh, but we will go with that. Our second speaker is Dr. Mostafa Abbaszadeh. They will be giving a talk on HPINNs. Gradient is not enough, you need curvature. Dr. Mostafa Abbaszadeh is an associate professor of applied mathematics at Amirkabir University of Technology in Tehran, Iran. His research focuses on solving nonlinear PDEs, exploring novel methodologies to tackle these challenges. Abbaszadeh also serves as the head of the Machine Intelligence and Numerical Data Laboratory, where he leads a team of dedicated students in applied mathematics. The lab is actively involved in developing innovative approaches for solving nonlinear partial differential equations. Recently, Mr. Rauf Zare Moayyedi and other students have been investigating the physics-informed neural networks method. Rauf has made significant strides in advancing this method through his extensive research efforts. With that short introduction, the floor is yours, Rauf, and you can start your presentation.
All right.
Everyone, very happy to be with you. We hope to have a good presentation for you. The topic of our presentation is about an efficient improvement for the PINN method. Rauf is one of the talented students who has both a bachelor's degree in mathematics and computer science. Rauf will start the presentation.
Thank you so much.
All right. Can you hear me? Is there any problem with my voice? All right. So from my side, I'm really grateful for giving time to me for actually presenting this work, and that's really great. And please ask a question whenever you have any questions. All right. Actually, we have made some changes to the name of the work, and the name is Aligning the Gradient is a Better Bias. And all right, from the first, I want to talk about loss surface in general deep learning problems. And as you know, for example, for a classification problem, we have some data points and some labels. But when you're approaching, for example, the decision boundary of the problem, then you know that, for example, actually the loss function is actually using the labels from, for example, your data point, and it's not appropriate to think your loss function should be 0 in the whole space, in the entire domain. And for example, this is a contour plot for some deep learning problem of, for example, classification, and this is really good. Loss surface, because we achieve great accuracy. But there's some differences in PINNs, because in PINNs, the ideal residual loss surface for us is the residual loss surface, which is 0 for the entire domain. This property, provides some other properties for us, kind of biases for us. The first one is zero gradient, and actually Professor Karniadarkis have a paper named GPINN, and they use this property for providing better results for solving PINN. There is two other properties, and the second one is zero curvature, and the third one, actually the gradient in the whole space have same direction. In this work, we are trying to use the last two properties for providing better results in this field. And actually, at the end, we make some connections with making gradient zero. Just for making sure, could you hear me? Because I'm not sure whether my connection is safe.
Yeah.
All right. All right. Now, what is our method? Actually, our the idea is making the curvature zero in the whole space. It's we are using a new bias to we add this term to our loss function to make sure the curvature is zero rather than just gradient. All right. Here I want to talk about some preliminaries for this talk, and please ask me questions whenever there was some questions. The first one is talking about HPINNs, and I just provide some short introduction to this topic because I'm sure everyone in this talk are really greater than me. But the first term is talking about the residual term in some PD problems, and the second one is boundary condition. And we have these two actually equations for each PD. And in the setting of HPINNs, we have some training data, some for boundary points, and some training data for residual points. And we have a loss function, and with minimizing the loss function, we hope that actually we learn the physical law behind these data points or dynamics. And here, L of R is actually the residual loss. And we know that in the ideal case, as I said before, the residual loss should be zero. And actually in each data point, our residual should be zero. All right. And the second one is actually Hutchinson trace estimation. And when you want to calculate the trace of a matrix, you could use this expectation to calculate the actual trace of the matrix. And you could, for example, estimate this expectation using law of large numbers, Monte Carlo method. And for this probability distribution, there's a lot of there are a lot of distributions that you can choose. But for our method, we use Radmacher distribution. The second one is Hessian vector product. As we know, the Hessian matrix is, calculating the Hessian matrix is computationally really, you need a lot of computation for calculating Hessian matrix, especially for high dimensional problems. And using that, saving that is all of those have made a lot of problems for in applications. Here we want to use Hessian vector product to calculate actually this quantity here, and we estimate this using finite difference estimations. And that's enough for this slide. And yeah, now our method is actually, we know that curvature have a relation with eigenvalues of the Hessian. And we know that the trace of the Hessian is actually some of the eigenvalues. So for this method, we consider the square of the Hessian, and we consider actually the trace of the square of the Hessian, which is the sum of the square of the eigenvalues. Now, with minimizing this quantity, you could make sure that your curvature is going to zero, because with minimizing this, you could actually make sure that each one of your eigenvalues are getting are approaching to zero. And so our problem will be calculating the trace of this quantity. And for calculating this quantity, we know that from a Hutchinson trace estimation that we could use this one. And finally, we could just calculate this quantity. And actually, based on the Hessian vector product, as I said before, we could calculate this easily. And just for our method, calculating this for large n is, computationally, you need a lot of computation. But in our method, we just consider one, direction, and I will talk about this in the later. All right, and there's some theoretical justification for this method. When you are using Taylor's theorem, if, for example, this X data point is your, for example, residual point, we want to make sure that how is residual point, how behave our residual loss function in the neighborhood of that data point. And we have this relation, and it is obvious by minimizing both gradients and the curvature, we can make sure that there is not much differences between training data and the data points that we haven't seen until now. And also, it is important to say that this coefficient here is of great importance because for high dimensional problems, it is obvious that minimizing the curvature is much important than minimizing the gradient. And it's just some theoretical justification. So from here, I want to talk about experiments, but there is some abbreviations. The first one is HPINN, which is from the paper of the Professor Karniodarkis, combining just gradient with PINN. The second one is CPINN, which is curvature plus PINN. And the third one is CGPINN, which is combination of both methods. And based on this slide, we could see that, generalizing, if you want to have a small residual error on the entire domain, you have to use both gradient and the curvature. All right, and this was the abbreviation. Now, I want to talk about experiments. For this presentation, I have provided two experiments. The first one is a damped harmonic oscillator. And I think this problem is really great for our method because in this problem, we just have one initial data point and there's no other boundary or initial more data points. And, you have to solve the problem just using residual points. And the second one is Koromoto-Sivashinsky. I've always had problem with this name, but this problem have some other properties. This problem have higher order derivatives, and also its boundary equation is kind of more complex because we have a first order derivative in the boundary condition. Right. So I will start with that harmonic oscillator, and I just provide the equation here. It's an ODE problem. And as I said before, we have just one initial point for this problem, and the initial point is have some first derivatives too. And it's the exact solution. And as I said before, here is our initial point. All right. So actually, this graph is the residual error on the entire domain. And you could see the graphs from 10 data points until 45 data points. And you could see here the trend of the CPINN and CGPINN is actually downwarding, but there's some fluctuating for GPINN and PINN. And for example, after 35 data points that you see GPINN is approaching two other methods, we could understand, I just provide enlarged graphs here. You could see that there's still much difference between these two methods. The residual error is getting actually much lower than GPINN for our method. And yeah, now for this graph, actually I provide.
Hi, Rauf.
Hi.
Can you go to the zoom in? What are the units? The zoom in, when you zoom in, why the units on the
actually, I thought maybe this part of the graph is misleading, so I just provide this section in this graph.
Yeah, but why the units? What are the units on the vertical axis?
Vertical axis is actually the residual error. The residual error for this, for this training model. For this, using just 35, for example, residual points, the error for GPINN and CPINN and CGPINN is reported.
But why the error is so big? Why the values are so big?
Actually, we are using really low data points. For solving this problem, you need to have about 200 or 300,
Right, but what is the error here? Because if you have not achieved, let's say, 10% error, this is the residual, right? But if the error is not sufficiently small, then it means that you haven't converged in any of these methods, because as you increase the number of points, all these methods converge to one value.
Yeah, that's true.
So you're very, very premature in some sense.
You want to say that for my plot, it was better to provide more data points or test them?
I mean, you're looking at a very premature convergence regime?
Actually, since my method, I will provide, just let me to go to final. As you can see here, for example, for just 30 data points, our method could converge to the exact solution. And that was the reason that I just checked that regime, low data regime. And as you can see here, with just 30 data points, CPINN and CGPINN could actually solve the problem. And that was the reason that I chose the low data regime.
Okay, good, thanks.
All right. So I want to get back to this section. But as we can see, as Professor Carney said, with increasing the data points, all of these graphs will finally converge to some region. But in low data regime, you could see that this method is kind of make really great, work really great. Right. The second plot is actually the actual error on the entire domain. And as you can see, CPINN and TGPINN is actually downwarding really fast, but GPINN and SPINN is kind of fluctuating. And moreover, again, enlarge this section. And as you can see, still there is much difference between these methods. And as you can see, where GPINN is about 1%, the error of GPINN is about 1%, but the error for CPINN and CGPINN is much lower than
Can you comment on the cost, because GPIN is twice as expensive as PIN? So what is CPIN? How much more expensive is PIN?
Actually, for calculating GPINN, you need another backbord to your network. And for CPINN, you need just 2 backbord to your network. It's not its computational cost is not twice, but for example, if I want to give you some numbers for training this method, a PINN needs about, I think, 5 minutes. A GPINN needs about 11 minutes, and our method needs about 18 minutes. They are kind of near each other, and there's not much difference, because for calculating our method, you need to just do another backbord more than GPINN, and there's not much difference between these 2 methods.
Okay, but the fair comparison will be to fix the cost, the work log time, and see which one of gives you the best accuracy.
You want to say in a fixed time, which one is getting you better accuracy?
Yeah, let's say for 20. Let's say for 20 minutes. If you use 20 minutes of work log time, which one of these? Because a simple example, you can do it.
Actually, for 20 minutes, our method is kind of much better than GPINN and SPINN. But in the next slide, I have provided some slides for showing how loss function is changing, and I think in that section you could see more properties of this method. But by the way, for 20 minutes, our method is much better than GPINN and SPINN. Because I told you, for 50,000 iterations, CPINN is just need about 17 minutes, and it's lower than 20. By the way, is there any other questions?
No, thank you.
All right. So you can see that actual error is much lower than this quant is much actual error of CPINN and CGPINN is much lower than GPINN. And here is actually. All right.
Please mention that we use the Google Colab. We don't have a good GPU.
Actually, for calculating all of these, I just use Google Colab, but I think yeah, that's it. All right, for dynamics of the training, you could see here how our method is working. It's just some empirical notes about the method, but it seems CPINN and TGPINN is actually trying to get out some minimal local minimal in the input space, but you could see that GPINN is just kind of growing, and when it falls down in some local minima, it could not get out here, or sometimes it diverged. But you could see that CPINN and CGPINN try to get out the local minima, and after a time, they have provided great, performance. And also here you could see CPINN and CGPINN are trying to get out the local minima, and after a while they get better than GPINN. And these two plots are the first one is for 30 data points, and the second one is for 40 data points. And these graphs are again for actually the last the last slide was about the residual loss. But this one is about, the loss, just the error term of the method. And as you can see here, CPINN and CGPINN again are trying to get out the local minima, and they converge after time, and they provide great results. And all right, and here I have provided some graphs regarding the loss of the training data. And you could see the trend that I have told before, that these two methods, it seems that these two methods are trying to get out the local minima of the problem. And actually, this is the result for just 30 data points. And as you can see, the usual PINN, it actually cannot learn anything with these 30 data points. And the interior points for all of these experiments are fixed. There's no difference between the interior points for this experiment or this one. All of these, for example, experimental setup are fixed. And as you can see, in the same iterations, we could get much greater results than PINN and GPINN. And as I said before, for this problem, this plot takes about 4 or 5 minutes. Running this method using PINN, we need just about 4 or 5 minutes. For this one, we need about 11 or 12 minutes. And for this one, we need about 17 or 18 minutes. And there's just 6 or 7 minutes difference between GPINN and CPINN and CGPINN. You have one inverse problem in GPINN.
One inverse problem, yeah. And it looked a little better, but yeah. Yeah, but I think the forward problem is actually more dramatic, and I think what you're showing here is really interesting, that that you can avoid bad minima by flattening the curvature. You can avoid flat minima, so that's a really good point, I think.
And I want to just say one point, and it's about 1.1 that I'm working on this project, and there's much more experiments that I have to run. And the problem is I'm just using Google Colab, and computationally it's too high for me. But by the way, of course I will provide some experiments regarding inverse problem. And I think this method, the most important point about this method is for higher dimension problems, because in higher dimension problems the curvature has much more has better role, and with minimizing that we could get much better results. And sampling and all of these things in higher dimensions are really hard. But using this method, I think we could, have really great results. And actually, currently, I'm running some experiments for a Poisson equation for 10D and 100 dimension. But yeah, it's just for here. Is there any other questions?
You can continue. Thank you so much.
All right, thank you too. So as you can see here, this method could provide much better results than other methods. By the way, the second one is Koromatos-Tivashinsky, and this method has higher order derivatives and some, first order derivatives for the boundary condition. And here is the exact solution. I'll just provide this because I use the exact solution for this one. All right. And here, actually, our domain for this problem is kind of large. It's from -10 to +10. And actually, I'm trying to solve some problem for larger domain. All right. And the exact solution for this, problem at t equals to 1 is this graph. All right. So these plots provide much better intuition, I think, regarding CPINN and CGPINN. And as you can see here, in all experiments, here I have provided much more data points to, that was first experiment. Here I decided to, just expand the experiment. And here from 50 data points to 120, you could see the trend, the downwarding trend of CPINN and CGPINN. And all right, here, in this slide, I just removed the PINN because it could be just misleading. And here you could see the difference between our method and GPINN much better. And also it needs to say that CGPINN is actually a combination of CPINN and GPINN. And you could see that, there is not much, there's no fluctuating like GPINN in CPINN and CGPINN. And here, the last two graphs were regarding residual error. But here we have the error on the entire domain. And as you can see here, again, there is downwarding, trend for CPINN and CGPINN. And actually, most of the experiments are really low. But you could see here that GPINN and PINN could not solve this problem in this data regime. And here I just removed the PINN, and you could see that GPINN and CPINN here. And all right, and here actually we could see some other trends. Here I provide actually the changes of the residual loss for about 85 data points. And as you can see here, we still have those, fluctuating that it is trying to get out the minima, local minima. But as you can see, the GPINN could not. And, in two cases, and there was just two random cases. I didn't arrange to, for example, provide these two plots. No, I just, based off the experiments, I tried to provide two regimes that they are kind of near. And 80-point data points, they are, at 80-point data points, there are much difference, but in 95, these two are kind of more, more near to each other. But as you can see here, GPINN diverge after a time, and PINN is awful. The reason that I do not provide the PINN is actually it makes, it provides some misleading, because I think by providing PINN, you could see this section properly. But you could see that GPINN could not diverge in this data regime. And, it's just fluctuating, but CPINN and CGPINN could, find its path to get great residual error. And we can see this trend for, error term. And the last one was about residual loss. This one is about the actual loss. And, we still could see that CPINN and CGPINN is trying to, getting out the local minima as still, converging to best possible solution with, with really low data regime. And the thing that I have said before about getting out the local minima, you could see here that CPINN and CGPINN is, this plot is regarding a lot on the training data. And you could see here, most of the time, it makes its training data worse to get out the local minima. But we could see not this same trend for GPINN, and GPINN just here have a spike. But, CPINN and CGPINN in the whole space, in the whole iteration, is trying to provide better results and getting out the local minima. Here I have provided two other experiments to show how, this method affects the curvature. This plot is actually domain of the problem, and these numbers are the residual of each data point. And if you note to this axis, which is the value of the residual in each data point, you could see the high curvature in this region, and also for GPINN. But when we go to, for example, CPINN and CGPINN, although it has the similar trend, but if we look at the axis, we could see that, for example, it's much more flatter than these two methods. And it's obvious that it is minimizing the curvature of the space. And this is actually the results for 85 data points. And as you can see, PINN could not learn much, and also GPINN, but CPINN and CGPINN, learn much better than these two methods. And actually, this was my presentation. And if there's any questions, I will be grateful to answer you.
Thank you so much for your talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Article related to CGPINN, and actually CGPINN is our method, and but GPINN, I'm not sure whether I understand, because GPINN is currently a published paper by Professor Courant. If you want some links, I can just send it here, but I'm not sure whether I understand the question.
Do we have any other questions? Fatima, you can look for like HPINNs, and I'm not sure
I
about
could send the link here.
Okay, thank you so much.
All right. Just let me...
George, do you have any comment?
Rauf, I have a question. So for the Kuramoto-Zhivadzinsky equation, did you try to run longer in time, because the difficulty is later in time when you get these chaotic patterns? That's where the difficulty is with the dynamics. We develop multi-scale dynamics, but you run for a very short time, so you cannot really see anything. So, but the real multi-scale nature of the solution comes around after actually time t equals 1 all the way to time t equals 10.
Oh, no, actually, I didn't run this, and but I could provide the results for this problem, and yeah.
Because this is where for all dynamical, nonlinear dynamical systems, when you run long time integration, that's where you would see perhaps a benefit, because the loss landscape becomes very erratic, very rough. So if you try to flatten it like that with the Hessian, with penalizing the Hessian, I think that would be an advantage for multi-scale systems and chaotic systems in dynamical systems in general. But for that, you need to have long-time integration.
For you said for what I need integral equations?
Well, the Kuramoto-Zhivadzinsky is one of them, but all these types.
Oh, all right.
It could be the Navier-Stokes, the same thing for Navier-Stokes. It could be any, but Kuramoto-Zhivadzinsky is a good example. There is a.
But you suggest me to just provide some other experiments regarding how the time after t equals to 1. Yeah.
Yeah. So in the paper with on causality for pins from Paris Perdikaris, he runs all the way to t equals 10.
Mm-hmm.
The Kuramoto-Zhivadzinsky. He does it in increments of time of units, like 1, or I don't remember if it's 0.5. But basically, you want to run it longer to see if the benefit is even bigger.
It will be great, and I will do the experiments.
Because right now one can argue that you could use more points, because the cost for pins is lower. So I can use RAR, residual adaptive refinement, plus more points for pins, and I can be more competitive than CG pins that you have. So it's not exactly a fair comparison, because at the end it's cost, right? So for given accuracy. So, but I think where your method would be really effective is when you go to strong nonlinear systems in the long time integration regime.
One point that I want to say that regarding this method is actually, I do not provide the exact, implementation of the method, but I'm trying to, for choosing those data points that I want to flatten the curvature, I'm trying to choose some data points which are making, this work worse. And I think it's another, another advantage of this method. And moreover, I was thinking to introduce all of these methods as a post-processing. For example, you do not have much data points and you train some PIN methods. You could use GPIN and CPIN and all of these as a post-processing method to, for example, make your accuracy better. But still, I do not provide enough, experiments to show that in this talk.
Yeah.
Do we have any other questions?
By the way, Rauf, just for your information, the paper on GPIN, the first author was a 18 years old high school student.
Oh, that's really interesting.
Yeah, if you look at the affiliation, he's from St. Andrews High School in Texas.
Actually, currently I'm 23, and I think he or she was 5 years, younger than me, and it's really interesting that it was kind of, disappointing,
No, not disappointing. It just happened to be that guy he knew. He was a high school student, but he knew the Alan Khan equation.
But that was really interesting. That I think
he's MIT. He's a student at MIT now. He worked with Lulu for his internship. That's how he did this.
Oh, that's really awesome. But of course, it was it was my pleasure to be in this talk or in this room, and it's really great for me to present this project to you.
Great.
Well, I believe we don't have any more questions. From the audience. Yeah, thank you so much for your talk.
You're welcome.
And yeah, thank you for accepting our invitation. Thank you for everybody for joining us today. I hope everybody has a great weekend ahead.
Yeah, thank you very much
for giving this time to me,
and yeah, goodbye from my side.